Okay, this section might be a little bit long, this PowerPoint, because I have to cover a lot of information. Okay, so let's begin. These are the topics that will be covered today: sets, subsets, proper subsets, operation on sets, intersection of two sets, union of two sets, disjointed sets, Venn diagrams, introduction to probabilities, basic concepts of probabilities, multiplication principle, permutations, and combinations. So let's begin with sets. Okay, sets. A set is a well-defined collection of objects. At first, I need to do a lot of vocabulary. Okay, so that's what I'm going to cover first. Examples of sets. A well-defined collection of objects. All the students in my math class, that's a well-defined collection of objects. Letters in the alphabet, that's another example of well-defined collection of objects. The collection of young adults, you see that's not a well-defined set. Why? Because there's no defined, what are young adults, from what age? So this is an example of a not well-defined set. Now, but if we say the collection of young adults between the ages of 18 to 29, well, now that's well-defined. So this is a set. Okay, now capital letters such as A, B, C, they use to name sets. And each object in a set is called a member or an element of the set. Okay, the set, the braces are used to, for sets. Set braces, right? So are used to enclose objects in a set. For example, A equals the set of the numbers 3, 4, and 5. And here's how you read it. Set A consists of elements 3, 4, and 5. The symbol, the symbol like an E, this symbol in red is an element of the set of. So this means it's an element of the set of. For example, the symbol not is not an element of the set. Okay, with a line across it. Now let me show you an example. This is set A, which consists of the elements 3, 4, and 5. Now 3 is an element of A, or 3 is an element of the set 3, 4, 5, which means 3 is in A. That's what that means. Okay. And this is how you read it. 3 is an element of A, or 3 is an element of the set containing 3, 4, 5. 3, 4, and 5. Okay, now 2 is not an element of A, or 2 is not an element of the set 3, 4, 5. Okay, that means that 2 is not in A. And here's how you read it. 2 is not an element of set A, or 2 is not an element of the set containing 3, 4, and 5. Okay, now definition and examples. Empty set. A set with no elements. And here's a notation. These symbols, like the O with a line across it, or the braces with nothing in there, that means empty set. Equal sets. Equal sets contain exactly the same elements. These are equal sets: 3, 4, 5, 5, 4, 3, or 4, 3, 5. The order does not matter when the sets are equal, as long as each same element is in every set. That means they're equal sets. Okay, now sometimes we describe a set by a common property of its element rather than by a list of its elements. The property can be expressed with a set builder notation. Okay, so for example, we have the braces. We have X, a line, and then X has a property of P. This is how you read it. The set of all elements X such that X has a property of P represents a set of all elements having the same some property of P. And here's more in detail. The set, you see that the set means the braces, right? Or the brackets. The set of all element X is the X right there. This line means such that. And then that means X has a property of P. That's how you read it. Okay? Okay, now, example. List the elements in the set given in the given set. A. The set X such that X is a natural number more than 5 and less than 8. So a natural number more than 5 and less than 8. So it's going to be 6 and 7. Why? Because it's saying the numbers more than 5 and less than 8. So it's going to be the brackets, 6 and 7. This would be my answer, what they're asking for there. Now for B, the set such that X is an integer and between -3 and 1, and 1's included. So this is going to be -2, -1, 0, and 1, because the less than here, the sign here means that -3 is not included, and this means here X is less than or greater. X is less than or equal to 1, which means the 1 is also included because of the line in the bottom here. That means it also can be equal. That's why this will be brackets, -2, -1, 0, and 1. Close the brackets or the braces. Okay, you need to know. Okay, guys, these are considered whole numbers. Whole numbers start with 0 and they go on for infinity. Counting numbers, they begin with 1 and they go on for infinity. Natural numbers are counting numbers, and you need to know that, because at times that might be asked as a question, and if you don't know what whole numbers are or counting numbers are, then there's going to be an issue there. So it's good to know what are whole numbers and counting numbers. Okay, now these are actually examples from homework problems from the book. It says here, state whether the statement is true. Okay, let's see. Let's see number 1. 3 is an element of the set containing 2, 5, 7, 9, and 10. That's false. And here's the reason behind it. 3 is not an element of the set. You see, 3 is not in the set. Number 2. 2 is an element of the set containing 2, 5, 7, 9, and 10. This is true because 2 is in this set. Okay, and 2 is an element of the set. Number 3, 6 is not an element of the set containing 1, 3, 5, 7, 9, and that's true because 6 is not in the set. Okay. Number 4, 4 is not an element of the set containing 2, 4, 6, and 8. This is false because 4 is in the set. Okay, now number 5. The set containing 1, 2, 3, 4 equals to the set containing 4, 2, 3, 1. This is true because every element in the first set is also in the second set. Or both sets have the same elements. Number 6. The set ABC equals to the set containing the elements A, B, C, and D. This is not true. Why? Because the first set, ABC, does not contain D. So that's not false. That's not true or false. And both sets do not have the same elements. The first set does not contain the element D. Okay, now number 7. All the whole numbers greater than 5 and less than 9 equals to 6, 7, and 8. That's true. Okay. Greater than less than 8 means the whole numbers between 5 and 9. Okay, now natural numbers. All natural numbers not greater than 4. This is not true or false. Why? Because 0 is not a natural number or counting number. Number 9. The set X such that X is an even integer between 5 and 19. We have 6, 8, 10, 12, 14, 16. Is that true? I don't think it is because it's missing the 18, so it's false. 18 is missing in the set. Number 10. The set X such that X is a vowel, which is true because A, E, I, O, U are all the vowels, so that's true. Okay. So now let's go to the next topic, which are subsets and proper subsets. Let's first get the definition. Universal set. It means a set that contains all the objects being discussed. Subsets and proper subsets. Okay, here's the definitions. A set A is a subset of set B. And here's how you write it. A is a subset of B, provided that every element of A is also in B. So in other words, every element in set A has to be in B. If not, it's not a subset. Now for the second one, a proper subset. A set A is a proper subset of set B. And here's how it's written. A is a proper subset of B if every element of set A is an element of set B, but B contains at least one element that is not a member of A. Okay? Right now I'll show you some examples. When A contains an element that is not in B, then A is not a subset of B, and we write it as A is not a subset of B. Okay, now let's do some examples. At times, the definitions might be a little bit confusing, but with examples, these are going to make sense. Okay, now here are more definitions that we're going to know. For any set A, the empty set is a proper subset of A, the empty set is a subset of A, and A is a subset of itself. So A is a subset of A. Okay. Examples, we have set A is A, B, and C. Set B contains the elements A, B, C, D. And set C contains the elements C, A, B. Okay, so let's answer the following questions. Okay, oh my bad, let me go back. Here we go. Here's how you read it. A is a subset of B, right? Because every element in A is also in B. Now let's do B. A is a proper subset of B. This is true because every element of A is an element of B, but B contains at least one element not in A, which is D. That's what we're describing the proper subset. Okay, now C. B is not a proper subset of A. Every element of B is not in A, right? So that's why this is correct. Every element of B, so every element of B is not in A. Okay, now A is a subset of C, which means every element of A is also in C, right? We have ABC and CAB. So anyway, in other words, these are also equal sets, right? And this is true because any set can be a subset of itself. Okay, where are we? We're here at E. A is not a proper subset of C because A equals C. And the definition of a proper subset means that, for example, here, the set A must contain, if every element of A is also an element of B, but B contains an extra element, at least one more element. And here, since these two are equal, that's why this is the correct notation with a line across it. Now, if the empty set is a proper subset of A, this is true, right? Because it carries here the definition that the empty set is a subset or a proper subset of any set. Okay. Okay, now, I believe this is from the homework. It says let A equal to -4, 0, and 4. The set of B equal to -3 all the way to 3, the integers. C equals to -4, -1, 0, and 4. D equals to 0. E equals to -4, the set E. And the universal set, which means U, is equal to -4, all the integers from -4 to 4. Here it says, insert the proper subset or not a subset to make the given statement true. Okay, now here we have A and U, right? So we're going to look at A. A has -4, 0, and 4, right? So let's go to U, -4, 0, and 4. So A is a proper subset of U. Okay. Now let's go to E. We have set E and set A. E is -4. And set A is -4, 0, and 4. So this one is the same thing as number 11. E is a proper subset. That's this is the reason why for number 1. But E is a proper subset of A. And here's why. Every element of E is an element of A. But A contains at least one element not in E. Number 13, we have A, we have E. So this one will be, is not a subset. A is not a subset of E. Every element of A is not in E. Elements 0 and 4 are not in E. Let's look at sets B and C. Sets B and set C. So again, these, right, every element of B are not in C. So this is going to be the not a set. I mean, not a proper set. So B, every element of B is not in C. Elements -3, -2, 1, 2, and 3 are not in C. So B is not a set. It's not a subset of C. I'm sorry about that. I got my tongue twisted. The empty set is a proper subset of A. Okay, it's a subset and a proper subset of any set from the definitions. Number 16, the set containing elements 0 and 1, this is blank of D. Let's go to D. So this will be the not, right? Not proper, I mean, not a subset. Okay. Now let's reverse it, right? We have D, which is the element is 0 and 0, 1. So this is going to be the symbol with a proper subset. There we go. Every element of D is an element of set 0, 1. But set 0, 1 contains at least one element that is not in E. That's why this is a proper subset. Now let's look at D, which is a set with a 0 in there, and B. So this is also going to be the proper subset because every element in D is also in B, and B contains more elements that are not in D. For A and C, this will be the not. I mean, this will be not the not. This will be the proper subset. A is a proper subset of C, because every element in A, right, is also in C. And C contains at least one element that is not in A, which is a -1. Okay, now list all the possible subsets of each given set. So let's do A first. Okay, recall. The set A is a subset of set B, provided that every element of A is also an element of B. So for A, right, so this is my solution, right? So we're going to start with the empty set. The empty set is a subset of 4 and 6. Now let's do it one at a time, right? With one element at a time. So 4 is a subset of the set 4, 6. Also 6 is a subset of the set 4, 6. And every set it's a subset of itself. Okay? So these are the subsets of the set of elements containing 4 and 6. The set with 2 elements has 4 subsets. Okay, now let's do B. So now, guys, we're going to start like in order, right? First, we're going to start with the empty set. Then we're going to do them one at a time. So set A is an element. Set A is a subset of the set A, B, and C. Set B is a subset of the set A, B, and C. And set C is a subset of the set A, B, and C. Now let's do them in twos. The set A and B is a subset of the set A, B, and C. AC, the set AC is a subset of the set containing the elements A, B, and C. And the set B and C is a subset of the set containing the elements A, B, and C. Now let's do them in threes, right? Every set is a subset of itself. So these are all the subsets. You see, if you notice, we're going to have 8. Okay, now, this is also like a definition, okay? The set of n distinct elements has 2 to the n subsets, okay? So I believe in the homework, if they don't ask you to list them, just to how many subsets are there, this is a formula that you use. But if they want you to list them, then you do how we did examples A and B. But for example, let's go back to A, right? Say, for example, they weren't asking to list them. How many elements are there? 2, right? So n is 2. So it'll be 2 to the second power will give us 4. You see, there's my 4 subsets. Look at B. We have 3 elements. So then my n is 3. So 2 to the third power will give us the 8. Now with the same concept, let's do 20 to 21. How many elements are here? 1, right? So this will be 2 to the first power, which is 2. So there will be 2 subsets. I jumped again a little bit. Number 21, we have three elements, so it will be 2 to the third power will give us 8 subsets. X is a whole number less than 5. So remember, whole numbers start with 0, so it'll be 0, 1, 2, 3, and 4. So it's going to be 5, right? Right, so 5 elements, so 2 to the fifth power, this will give us 32 subsets. This will be kind of hard to do, right? Because at times we tend to, if we don't have some kind of order, like to list them, we're more likely we're going to make mistakes. So that's why most of the times instructors might give this in the exam, but they're only going to give you like maybe at the most 3 or 4 elements. Because with 4 elements, you're going to get 16. Why? Because 2 to the fourth power will give you 16. But it's real rare for them to give you, to list them with 5 elements, because it's going to be 32 subsets. Okay. Okay, now these are operations on sets. Given a set A and a universal set U, the set of elements of U that do not belong in A is called a complement. The complement of A is written like A prime, that's read A prime or not A. Example, let the universal set U equal to 1, 2, 3, 4, all the way to 12. The set A is equal to 1, 2, 3, 4. So here is like with a Venn diagram, right? This is U, this is A, and here on the outside of A is not A, or A complement. Now let's fill it out. Find not A. Hey guys, so not A means that I'm going to go to the universal set, and it's going to be not 1, not 2, not 3, and not 4. So not A will be whatever's left. It'll be 5 all the way to 12. Okay, and here's how you do a Venn diagram representing the same complement of A with a universal set given. Right, so this is U, that's A. So what's in A? It will be 1, 2, 3, 4. Right, this is set A. Now, not A means they're in the universal set, but they're not in A, so it's going to be 5, 6, 7, 8, 9, 10, 11, 12. That's how you represent this problem, right, in a Venn diagram. Okay, now, this is called intersection of two sets, which means and. So every time you hear the word and, for example, given two sets, A and B, this is a notation, and it means intersection. The set of elements belonging to both set A and B is called the intersection of the two sets. Written and A, this looks like an upside down U, right? But this is not a U, right? This is a symbol, but that's the way it looks like. Elements belonging to both sets. Okay, now, at times, students do not understand about intersection. So, in red means how I explain at times for students that do not understand about intersection. So I just tell them, what do they have in common, both sets? And at times, that makes better sense to the student. But every student is different, so every student should use what's easier for them. Okay, now, example. Let universal set U equal to 1 to the counting numbers from 1 through 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And set A is a set containing elements 1, 2, 3, 4. and set B contains the elements 2, 4, 6, 8. So now let's answer the following questions. Find A and B, or A intersects B. Okay, which means what does A and B have in common? They have in common a 2, right? They have in common a 4. So that's my solution, the set containing the elements 2 and 4. How do we represent that in a Venn diagram? Okay, that's U. This is set A. This is set B. And here is the intersection here, guys. This is A intersects B. Now, let's do this very same problem, but with a Venn diagram. That's U. Okay, so first, we're going to start here with the intersect. So the 2 and the 4 go in here, right, in the intersection. Now, we go to set A. Set A was 1, 2, 3, 4, right? So the 1's missing, and the 3 is missing, so the 3 have to be here. This means that 1, 2, 3, 4 are in A, right? This is A here. And this is going to be set B. And this section here is where they both intersect, or where they both have in common. So now let's go to set B. Right, this is B, so B is missing we got the 2, the 4, we're missing the 6, we're missing the 8. This is how you represent the Venn diagram, okay? But now we have to represent what's not in set A and B. So all the numbers that are not here have to be here in the outside. So we have 1, 2, 3, 4, we're missing the 5. We got the 6, we're missing the 7. We have 8, we're missing the 9, so 9 has got to go there. The 10, the 11, and the 12. Here's a representation of the Venn diagram with the given scenario. Okay. Disjointed sets. For any set A and C, if A and C are disjointed, then A and C is the empty set, or A does not intersect C. Okay, that's what that means, is the empty set. Let's do another example. So example, let universal set U equal to 1, the same as before, 1 through 12. Set A is same as before, 1, 2, 3, 4, and set B are the elements 2, 4, 6, 8, but they added C. Set C contains the elements 5, 7, 9, and 11. So let's answer the following questions here. Find A intersects C. What does A and C have in common? Nothing, right? We have the 1, 2, 3, 4. They're not here, so that means it's going to be the empty set. That's your answer for that one. How do we represent that? These are called disjointed sets. That's universal set. That's set A, and that's set C, right? They don't have nothing in common. So set A contains 1, 2, 3, 4. Let's do here we go. 1, 2, 3, 4. That's set A. And set C contains 5, 7, 9, and 11. And the rest have to be right in the outside. We have 1, 2, 3, 4. The 6 is missing, so it goes in the outside. 6, 7. The 8 is missing, so we have to put 8 somewhere. 9 is there. The 10 is not there, so we have to put it here on the outside. There's my 11s, and the 12 is missing, so we have to put it in the outside. This is the representation of this given scenario here. Okay. Union of two sets, which means or. Given two sets A and B, the sets of elements belonging to set A or B is called the union of the two sets. And here's a notation. A, that's my symbol, like a U, and then the B. This is what I tell my students, because at times this can be a little bit complicated for students. So I tell the students, you list all the elements of both sets, but do not repeat them. Okay. Again, example, the same scenario as the previous example, but we only have sets A and B, and there's my universal set. So find A, union B. So I tell my students, to write everything that's in A first. Write A is 1, 2, 3, 4. Now you're going to go to B. And if it's already here, you don't write it again, right? You don't repeat it. Is a 2 here already? Yes, so we don't write it again. Is a 4 there? Yes. Is a 6 here? No, so we have to put the 6 inside here. Is the 8 there? No, it's not, so we have to put the 8 also. So that's my set of A or B or A union B. And here's represented with a Venn diagram. That's set A, that's set B. The union will be, right, so this is a union of both of them together. Again, now let's do it by actually putting in the elements. So A, right, what they have in common? They have in common the 2, right? We have to put the 1, let's see here. Set A is 1, 2, 3, 4, right? The 2's in here because they have it in common. The 4 goes here inside, they have it in common. So that's a set of A, 1, 2, 3, 4. Now, set B, the 2's already right, so we're going to put the 6 and the 8. So this is the representation of A union B, but now we have to put the numbers or the elements that are not in sets A and B. So the 5 is not in here, so we have to put it out there. We have 1, 2, 3, 4, the 5, the 6, the 7 is not here, so we have to put it out there. The 8's here already, so we have to write it. The 9 is not there, so let's put it out there. The 10 is not there also. And the 11 goes out in the outside. And the 12 goes in the outside, but inside the rectangle, which means this is the universal set. This whole thing is inside. Okay, now operation on sets. Let A and B be any set with U signifying the universal set. Then the complement of A is written in this form. A naught or A complement. Okay, that's a notation. The complement of A is equal to the set X such that X is not in A and X is in U. This is how you write it. This is how the Venn diagram. This is A, that's not A. The intersection of A and B. Right? There's my notation, and here's the Venn diagram, right? A and B means where do they intersect? The union of A and B. There's my notation, and set block notation, and here's my Venn diagram. A union B. Okay, now, I believe this is also from the book, okay? It says exercises. Let U equal to the set containing the elements A, B, C, D, E, 1, 2, 3, 4, 5. And set X has the elements A, B, 1, 2, 3. And set Y containing the elements B, D, 1, 3, 5. And Z containing the elements B, 2, 3. Now it says here, list the members of each of the given sets using set braces. Okay, now, before we do that, right, because we have to find the complement of X, complement of Y, so let's do it here on the side here. That way we have all the work here. So that's my set X. Now the complement of X is going to be C, D, E, 4, 5. How do we get that? We go back to the universal set. And whatever elements are in X, we scratch them out because it means not A, not B, not 1, not 2, not 3. So what's left is C, D, E, 4, 5. That's my set Y. This is my set, the complement of Y or not Y. And again, the same way, right? We go to the universal set. So not B, not D, not 1, not 3, not 5. So this is what's left. The elements A, C, E, 2, 4. That's Z. Right, so now let's start because here we don't have to find the complement of Z, just only X and Y. So now this will be easier to observe because everything's here on the right. What does X, what's X and Y means what, where does X and Y intersect, or what does X and Y have in common? Let's go here on the right. Do they have an A? No. A B? Yes, they have a B in common. A 1? Yes, a 1 in common. 2? No. 3? Yes, they both have a 3. So that's my solution for the set of X and Y, or X intersects Y. Okay, now number 24. Let's do X union Y or X or Y. That's what that means. And like I said before, we're going to put everything that's in X, right? Because that's first. We're going to put everything in X, which is A, B, 1, 2, 3. Now we're going to go to Y. If it's already in there, in here, we can write it again. Is a B already in here? Yes. Is a D in here? No, so we have to put D. Is the 1 already there? Yes, it is. How about the 3? Yes, right there. How about the 5? Oh, no, there's no 5, so we have to add the 5. So that's my solution. And most of the time, the back of the book has them in alphabetical order and also in order, also numerically. But this answer are both the same because they're called equal sets. Okay, now the complement of X, right? The complement of X, we already have it over here on the right. Okay, now the complement of X intersects the complement of Y. So we go here on the right. What do X and Y have in common? They have in common a C, right? They have in common an E and a 4. So that's my solution. Now let's go to 27. The complement of X intersects Z. So let's go here on the right. What does X, complement of X and Z have in common? Right? Does it have a C? No. D? No. E? No, it's not here. A 4? 5? No, so it's going to be the empty set. Right? Or these are the two symbols for empty set. Okay, now number 28. 28, it has X union parentheses Y intersects Z. So here, guys, we also have to follow PEMDAS. We have to do what's in parentheses first. So we're going to go to Y intersects Z. What does Y and Z have in common, right? Let's put it here on the right. Does it have an A? Do they have a B? Yes, they have a B in common. Does it have a D? No. A 1? No, it's not in Z. A 3? Yes, they have a 3. A 5? No. So the answer will just be B and 3. So this is Y intersects Z. Now we have X union with a set containing elements B and 3. So like I said earlier, we're going to write everything that's in X first. Right? X is A, B, 1, 2, 3 from here on the right. Now, if the B's already in here, we can write it again. Is a B here? Yes, it is. Is a 3 inside here? Yes, it is. So this is my solution, just like that. Okay. Okay, now let's do from the Venn diagram. List the universal set U, set A, set B, and set C. Set A intersects B, set A intersects C, and set B intersects C, and set A intersects B and C. So let's start here. Right, so this is my universal set. So let's first start. Okay, this is my U, right? My U universal set is A, B, C, D, E, F, G, right? All the elements that are here. Now set A is going to be A, D, E, G. Set B is going to be B, D, G, F, right? All these here, all these elements here. And C is going to be C, E, G, F, all these elements in type C. Okay, now, where do they intersect? What does A and B have in common? A and B, they have in common a D and a G. What does A and C have in common? A and C are these two here. They have in common an E and a G. Right, these two here. How about B intersect C? What does B and C have in common? Right, so these two sets is going to be the G and the F, or F and G. Okay, now where do the other sets intersect? It's going to be right here where the G is. So the answer will be G. Okay. Okay, now I believe this is the last problem for this section here, and then we'll move on to probabilities. So this is number 30, I guess, from this section here from the book. It says 60 people were contracted and responded to a movie survey. The following information was obtained. Okay. 6 people like comedies, dramas, and science fiction. 13 people like comedies and dramas. 10 people like comedies, science fiction. 11 people like dramas and science fiction. 26 people like comedies. 21 people like dramas, and 25 people like science fiction. So we have to answer A, B, and C, and D. So for A, the first one is to draw a diagram, a Venn diagram illustrating the survey. Okay, so let's do it then. There's my universal set, right? There's my U is 60, right? Because 60 people. So let's see B comedies. That's my set C. Let D be dramas. That's my set D. And set S be science fiction. This is my set S. Now, I guess the key thing when you do this type of problem is that you always start where all three intersect, right? That's why that's in red here. 6 people like comedies, dramas, and science fiction. So we're going to start right here at the middle. There's my 6. Now then we go with intersection between 2 of them. Let's start with the intersection of C intersects D, right? That's the second part here. So we got C and D, right? So it's going to be this section here. So this is total of 13. We already got 6, so this has to be 7. Okay. 10 people like comedies and science fiction. So 10 people, right? So comedies and science fiction will be this part here, this section here. So we got 6, right? But it's supposed to be 10, so this has to be a 4 there. See, there's my 4. 11 people like dramas and science fiction, right? So dramas and science fiction will be these 2 here. So they're talking about right this area here where they intersect. So it's equal to 11, right? So we got 6, we need 5 to be 11, so 5 is missing. Then we go here to 26 people like comedies, so then we go to comedies. All this is, right? All this is comedies. So all this has to be 26. We got 4, we got 6, that's 10, that's 17. So we subtract 26 minus 17 will give us 9. Then they're saying that 20 people like dramas, right? So dramas will be here D. So this is D here, 21 people. We got 5 and 6 is 11, plus 7 is 18. So this should be 3, because 21 minus 18 is 3. And then 25 people like science fiction. We got 4, we got 10, 15, so we're missing 10. So that was a 10 there. Now we have to find out what's not in the sets, but it's in the universal set. So what's out here? So we're going to count all these numbers and subtract it from 60. Okay, this is what x equals to. So we have 9 plus 7, right? We have 9 plus 7 plus 6 plus 4 plus 3 plus 5 plus 10, which is 44. So 60 minus 44 is 16. So there's 16 people or 16 people that took the survey that didn't like none of the movies. Okay, now let's answer the questions, right? This is the answer for A. For B, how many people surveyed like comedies, right? So we go to comedies right here, but neither drama nor science fiction. So how many people didn't like drama nor science fiction, but only comedies? So the answer will be 9. See, 9 goes there. For C, how many people surveyed like dramas and science fiction, but not comedies? Okay, so let's go with dramas and science fiction. Dramas and science, so it's going to be dramas and science fiction. So it'll be this right here, right? But not comedies. So the answer should be, right? So it'll be 3 plus 5 plus 3 plus 5 plus 10, which is equal to 18. Again, we're going to go here, right, it says here, let me go back to dramas and science fiction, right? So that's why it's going to be only these here, right? Because not these here, guys, not comedy. So we go to here, so it's going to be only 10 plus 5 plus 3. That's why it's 18. How many people like none of the movies? So the answer will be 16, right? The 16 that are not inside the sets here. So my answer is 16. And I believe this is a problem that most instructors assign during the semester for this class here. So it's good to go back and look at this part of the PowerPoint to understand how to do these problems here. Now comes a new section. Okay, this is called probabilities. Random experiment. All that means that it's a process by which we observe something uncertain. After the experiment, the result of the random experiment is known. Sample space. Sample space is denoted by the letter S. It means the set of all possible outcomes of a random experiment. And the next examples, we're going to find the sample space. Okay? For example, examples of sample space. For a coin flipping, the sample space is, right, if you flip the coin once, it's going to be at heads or tails. That's why this is my sample space, heads, tails. Rolling a third die means a die has only six sides, so it's going to be 1, 2, 3, 4, 5, 6, because it can land on any one of these numbers here. So it's only 6. Okay, at times, guys, it's easier to draw a tree diagram to find the sample space. Example, find the sample space of flipping a coin twice, right? So here we go. Flipping a coin twice, so there's once, right? It can be heads or it can be tails. This is one flip. Now comes my second flip. From the heads, it can be again heads or tails. And if it was tails first, then it can be heads or tails again. Okay. So as my sample space is going to be heads, 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 tails, tails, heads, and tails, heads again, and tails, tails. Okay. Now here's my sample space. Heads, 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 tails, tails, heads, and tails, tails. Okay, now an event. An event is an outcome or a set of outcomes of a random experiment. Okay, so let's do an example. An event is a subset of a sample space. Okay, for example, if a sample space of flipping a coin is heads or tails, then one event is heads, which represents the outcome of heads. Checkpoint. Okay, suppose a die is tossed. Now they want you to write the event. Write the given event and say notation. Right? If a die is tossed, it can only be 1, 2, 3, 4, 5, or 6. The number showing is less than 3. Right. So this is right. So my solution, right? So we go to the sample space. So then the number showing less than 3 is going to be 1 and 2. Okay, that's my answer. For B, the number showing is 5, so it's going to be just 5 in there. See, the number showing is 8, right? It's going to be the empty set because it's only 1 through 6 for a die being tossed. The number showing is an even number, right? So even numbers are going to be 2, 4, and 6. So these are examples of the event, of this event to take place. Okay, now here's the basic probability principle. You see, guys, here is a number in the event, and here's a number of the sample space. That's the probability of the event to happen. Okay, let's read the definition. Let S be the sample space of equally likely outcomes, and let the event E be the subset of S. Okay, so here we go. By the definition, the probability of an event is a number that indicates the relative likelihood of the event. The number of E is the number of elements in the event, and the number of S is the number of elements in the sample space. Checkpoint. Here we go. Suppose a single fair die is rolled with a sample space S equals to 1, 2, 3, 4, given the probability of each of the following events. The die shows an even number, right? So that means it's 2, 2, 4, 6, right? So it's 3 elements. So this is going to be, that's my event, that's my sample space, is going to be 3 over 6, which will be 1/2. Die shows a number less than 10. So that's going to be all the numbers, right? It's going to be 1, 2, 3, 4, 5, 6. That's my sample space. It's 6, so it's going to be 6 over 6 is equal to 1. The die shows an 8. None, right? So it's going to be 0 elements. So it's going to be 0, over 6, which is equal to 0. Okay, that's how we do these type of problems here. Okay, now, checkpoint. A single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen, a diamond, a red card, or a face card. At times, there are students, especially nowadays, that they don't know how the cards look like because they don't play cards no more. Like, for example, when I was growing up, we used to play cards all the time. So I know exactly what some cards look like. But for the students that they don't play cards, I'm going to show you like a visual presentation here. So for example, this is a set of cards, right? 52 card deck. There's also 2 jokers, but the jokers are not included here. So there's total of 54 with 2 jokers, but the jokers most of the times they're not included. These are called clubs. There's 13 clubs. These are called spades. There's 13 spades. These are called the hearts. There's 13 hearts. And these are called the diamonds. There's 13 diamonds. That's why there's a total of 52. Okay? Okay, now, there's 26 black cards because 13 plus 13 is 26. And there's 26 red cards because all the hearts and all the diamonds are also 26. Okay, now, there's 3 face cards for each suit. This is called a suit. The suit of clubs, the suit of spades, the suit of hearts, the suit of diamonds. Okay, what are face cards? Face cards are cards that have a face. For example, those are face cards, right? They all have a face. This is called a jack, the queen, and the king. Every suit has the same face cards, but only with the proper suit. For example, these are the suits of spades. There's also the same thing with the suit of hearts, the suit of diamonds, and the suit of clubs. So there's going to be, so for example, for the APA, right? I want to find the probability to draw a queen. This means like this, guys. Say that you have all the cards face down, right? What are the chances for you to draw a queen? That's what they're asking for. We know that the sample space is 52. So the probability of a queen will be 4, right? Because there's 4 queens over the sample space, which is 52. So 4 over 52, then you have to reduce to will be 1 over 13. So that's my solution, what they're looking for. For B, a diamond, right? A diamond, we know there's 13 diamonds. So 13 over the sample space, which is 52. Then we reduce, will give us 1/4. A red card. Okay, we know there was 26 red cards, right? So 26 over the sample space, 52, so it's going to be 1/2. Now, D. It says a face card or an ace. So face card or an ace, right? So how many face cards are there? There's 12, right? 12 face cards. There's 3 on each suit, and there's also four aces. There's the ace of diamonds, the ace of hearts, the ace of spades, and the ace of clubs. So it's going to be +4 over the sample space, which is 52. That'll be 16 over 52. You reduce it, give us 4 over 13. This is how you work these type of problems. So this is a probability, 1 over 13, 1 over 4, 1/2, and 4 over 13. Okay, now, this is an example from the book, and it's also something similar. It's assigned also for homework. Okay? It reads, when playing American roulette, the croupier, which means the attendant, spins the marble that lands in one of 38 slots in a revolving turntable. The slots are numbered 1 to 36, with 2 additional slots labeled 0 and 00 that are painted green, right? Because here they are, the painted green, 00 and the 0. Half of the remaining slots are colored red and half are black. In roulette, the slots labeled 0 or 00 are not considered as odd, as even or odd. Now here we go. Find the probability that the marble will land on a red or even. So here we go. Okay, so let's do solution. Let the set of red equal to R. Let the set of E equal to even. Right? So the R, right? So all the red cards, I mean all the red slots are here. I counted them all the way around. So all these numbers that are red in the turntable, I just list them right here. Now all the even numbers right? I also listed them here with a specific order and everything. So now, here's what we're looking for. Here's the formula that we're going to be using. This is called the probability of R union E, right? Because red or E equals to the probability of R plus the probability of E minus the probability of R intersects E. So here's this, there's total 38 slots, 18 black, 18 red, 18 black, 18 even, and 18 odd. Okay, so let's do this. And red and even. Red and even, there's 8. So then the probability of red, so this is going to be right. So the probability of red is 18 over 38, right? Because there's 18 red. Plus even, there's also 18 even over 38. Minus the ones that are red and even, right? Red and even means the ones here. You see this red and even, there's 1, 2, 3, 4, 5, 6, 7, 8. So that's why it's going to be 8. So 8 over 38. So we get 28 over 38. So this is my solution, 14 over 19. So the probability that the marble will land on a red or even is 14 over 19. Okay, example 2. Suppose, I know it's already time, guys, it's already 4 o'clock, but let me go ahead and see if I can finish it, because I believe this is really important information, especially for a 5-week course. Okay, example 2. Suppose 2 fair dice are rolled. Find each of the given probabilities. The first die shows a 2, or the sum of the result is 6 or 7. And B, the sum is 11, or the second die shows a 5. Okay, solution for part A. So here, guys, we're going to get says let A represent the event. The first die shows a 2. Let B be the event. The sum is 6 or 7. So let's get a picture of all the possible ways the dice can be. So here's the example for A, right? It says the first die is 2, right? So all these is what they mean, right? The first die is 2. You see, we have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So it's going to be all these in red. That's the event A. The event B is that the sum is 6 or 7, right? So this is all, the sum is 6, all these right here across, and this the sum is 7. So then, how many, right? So for A, right, how many is the first die 2? So it's going to be 6. Right, then my sample space is 36. This will be 6. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And where do they intersect? Right, so it's going to be 6 over 36 plus 11 over 36 minus, and where do they intersect? It's going to be there, right? What they have in common, where they intersect is going to be 2, 4, and the 2, 5, which is going to be 2. So it'll be minus 2 over 36. So this is the answer, 15 over 36. We simplify. The answer will be 5 over 12. So that's the answer for A part, 5 over 12. Okay, now in a similar manner, let's do part B. The sum is 11, or the second die shows a 5. So for part B again, those are the combinations there. So we have a sample space of 36. So again, here the same formula. So we're going to let A represent the event. The sum is 11. So only these two are 11. These two here, 5, 6, and 6, 5, which is only 2. Now we're going to let B represent the die. The second die shows a 5. So the second dice of 5 will be all these right here. All right, second dice of 5. See, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, and 6, 5. So it's going to be all these right here. So it's going to be what? 6. Now, where do they intersect? They intersect there, and that's it, right? Just there. So then just plug everything in. So it's going to be 2 over 36 plus 6 over 36 minus 1 over 36. The answer will be 7 over 36. That's your solution for part B. Okay, now complement rule. For any event E, the probability of not E equals to 1 minus the probability of E. And the probability of E is equal to 1 minus the probability of not E, or the complement of E. And also odds in favor. The odds in favor of an event E are defined as a ratio of the probability of E to the probability of not E, or the probability of E divided by the probability of not E. So let me show you what they mean here by odds in favor. Right? They're talking about these two here. So the probability of E is equal to the number of the event over the number of the sample space. And the probability of the complement of E is equal to the number of the complement of E over the sample space. So here, guys, right? So we put the first two first, right? The numerator first. Then we're going to multiply the second fraction. We flip it, right? So these two they cancel. They're equal to 1. So it leaves the number of E over the number of the complement of E. This is really the solution, right? Instead, we can go from here to here. We skip all the middle part. So let's do an example of the odds in favor. It says a marble is drawn from a box, 3 yellow, 4 white, and 8 blue. Find the odds in favor in drawing a given marble. Solution. Right, so there we have 3 yellow, 4 white, and 8 blue. So the odds in favor in drawing a yellow, which means yellow over not yellow. That's what it's saying here. So how many are yellow? Yellow will be 3. Not yellow will be 4 plus 12, right? Because the white and blue are not yellow, which are 4 and 8. So the answer will be 3 over 12, 1/4. But we have to write it as 1, 2, 4. That's what that means. This is what they want. This notation here. The odds in favor in drawing a blue. So it's going to be blue over not blue. How many are blue? 8. How many are not blue? Is 3 and 4, because the yellow are 3 and the white are 4. So it'll be 8 over 7. So the odds in favor for the blue will be 8 to 7. Now see, the odds in favor of drawing a white. So how many are white over not white? So it's going to be 4 over 11, or 4 to 11. That's how we work these problems out. Okay, now, let's see here. Here we have exercise 47 to 54 on page 435 from the 1324 book. Since your data from the 2016 General Society survey can allow us to estimate how many hours people who classify their work status as part-time or full-time actually worked in the last week. Use the following table to find the probabilities of the event. Okay, now, here, what my sample space will be, right, so this is my sample space, 1591. So for 47, right, a full-time worker. Full-time workers, so how many are full-time workers? We go here, right, to full-time workers, all the way across, will be 1,271. So this will be 1,271 over 1591. The answer will be 0.7989. Most of the times on these problems, they want you to round off to 4 places. Now let's do 48. Part-time worker. So part-time workers, we go here to part-time workers, so it's going to be 320. That's why it's 320. So it'll be 320 over 1591. Approximately will be 0.2011. Number 49. 50 or more hours is 370. No, 50 or more hours will be 393. Right? Because there are all these right here. 393. So it'll be 393 over the sample space, which will be 393 over 1,591, approximately 0.2470. Number 50. Work 0 to 19 hours, right? So 0 to 19 hours will be 106. It's going to be 106 divided by the sample space, and approximately will be 0.0666. Now let's do let's do here. I think number 51. Part-time worker and someone who worked 40 hours or more. So here, guys, is part-time worker. We're going to go here. Right, part-time worker and someone who worked 40 hours or more. So 40 hours or more will be these two here. So it's going to be the 49 plus the 21, right? These two here. It'll be 70 over 5091. Well, approximately will be 0.0440. Now this is number 54. Okay, 51 and 52 are the same, and so forth. So I'm going to do one example of each one. So 54 has the or, right? Is the or, which means, right? So it's good to use this formula. Right, part-time worker, right? So we're thinking about these workers here, part-time workers, right here. Part-time workers or someone who worked 20 hours or less. So 20 hours or less will be these two here, guys. Okay, so it's going to be 320, right? So 320 plus the 106 and 129, but not these two here. Again, I'm going to show you how to do it just by looking at, just by observation, and then we use the formula here. So the 320 came from the total part-time workers. And who work 20 hours or less will be, right, this is 29 hours, another way, because they work from 0 to 29 hours. So it's going to be these two here. So, but the 77 and the 87, they were already counted on the 320. That's why it's going to be 320 plus 106 plus 129 minus these two, because they were already counted before with the 320. Okay, now here's another way by using this formula here. They represent 20 hours or less, and they represent the part-time workers. So how many are the part-time workers, right? Is a 320, right? We got it from here, 320. The ones that work 29 hours or less will be the 106, which is from 0 to 19 hours, and the 129 from 20 to 29 hours. So this is a set, the set B right here. Minus, where does A and B intersect, will be these two here, the 77 and 87. Like I mentioned earlier on the example here on the left, that we don't count these twice because they already counted with a 320. So it'll be 391 over 5091, approximately will be 0.2458. Okay, now, these are called multiplication principles, permutations, and combinations. We're almost done here, guys. We need up for like another 5 to 10 minutes, but thank you for your patience. This is suppose n choices must be made with m1 ways to make choice 1, m2 to make choice 2, and so forth. So here's how we work this definition with multiplication principles. So in other words, we're going to multiply the number of the first choice times the number of the second choice, and so forth. Okay, so here we go. It says how many different heating cooling units are possible if the owner has 3 choices for the efficiency ratings of the furnace, 3 options for the fan speed, and 6 options for the air condenser. Use the multiplication principle. So number of choices for efficiency rating times the number of choices for the fan speed times the number of choices for the air condenser. So how many are here? 3. Number of choices for the fan speed was also 3. And the number of choices for the air condenser was 6. So it's going to be 3 times 3 times 6, which is 54. That's how many choices, or how many ways they can be chosen. Okay. 54 different units are possible. Okay, now, this is number 28 from page 477. It says the United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are supposed to be no restrictions, on the digits used? How many will be possible if the first column, if the first number could not be a 0? Okay, so we're going to put the 10 digits, make all the numbers from 0 to 9. So here, right, no restrictions. So right, because we have 5 slots because there's a 5-digit zip code. So how many numbers can go here? Right? These are all the digits here, 5-digit zip code. 10 can go there, right? Because any number can go there because there's no restriction. So it'll be 10 times 10 times 10 times 10 times 10. So it's going to be 100,000 possible zip codes. For part 2, the first digit cannot be a 0. So right, so for the 10 digits, it cannot be 0, so there's none left. And then 10, 10, 10, and 10, because the only restriction was with the first digit. So we multiply those out, so we get 90,000. Okay, so 90,000 possible zip codes. Okay, now number 30, again, page 477. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Okay? So no, 26 letters on the alphabet and 10 digits make all the numbers. How many different license plates are possible with this arrangement? So we're going to put 1, 2, 3, 4, 5, 6, right? The 6, because it's going to be 3 letters followed by 3 numbers or 3 digits. So how many letters are there? 26, 26, 26, right? Because there's no restrictions. And it'll be 10, 10, 10. Multiply them out. So we get something like 17,576,000 possible arrangements. Now for B, when the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plates were possible then? So now, right, they were reversed. So 3 digits followed by 3 letters. So again, that's the only restriction. So it's going to be 10, 10, 10, and 10, and 26, 26, and 26. So we get the same answer as part A. Now for C. Several years ago, the numbers described in part B were also all used up. The state then issued plates with 1 letter followed by 3 digits and 3 letters. How many new license plates numbers will this arrangement provide? So this is right, 1 letter followed by the 3 digits and then followed by the 3 letters. So it'll be 26 times 10 times 10 times 10 times 26 times 26 times 26 times 26. Multiply them out. We're going to get something like 456,176,000. Imagine, guys, like example B and example C here. We only added 1 letter. Look by how many more possible arrangements increased by. Like almost like 430,000 or 440,000 more. Yeah, just by adding another letter. Okay. Okay, now let me go to the next. Okay, now this is called factorial. For any factorial number, n factorial equals to n minus 1, n minus 2 until you get to 1. By definition, 0 factorial is equal to 1. Okay, checkpoint. Evaluate 4 factorial, 6 factorial, 1 factorial, 6 factorial, or 4 factorial. A 4 factorial, it will be the same thing as 4 times 3 times 2 times 1, which will give us 24. For B, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1, will give us 120. 1 factorial will just give us 1. Okay, now for D part, 6 factorial divided by 4 factorial. So 6 factorial will give us 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial will give us 4 times 3 times 2 times 1. So these cancels becomes 1, right? 1 divided by 1 is 1. That's also 1. That's also 1. And it's also 1. So anything by times 1, right, will be 6 times 5 times 1, which will give us 30. So this is the answer for 6 factorial over 4 factorial. Now these are called permutations. A permutation of set of elements is an ordering of the elements. For instance, there are 6 permutations or orderings of the letters A, B, and C. And those are the 6 ways. Okay, now, the order matters. For example, A, B, C, and C, B, A are 2 different orders. That's right, in permutations, the order matters. Example 3. How many batting orders are possible for a 9-person baseball team? Solution, there are 9 possible choices for the first batter, 8 possible choices for the second batter, 7 possible choices for the third batter, and so forth. So it's going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 362,180, or it's going to be 9 factorial, right? Same thing. And that can be put in the calculator also, guys, 9 factorial. But it's always good to know it by hand. Okay, now this is called permutations. If n PR where r is less than or equal to n is the number of permutations of n elements taking r at a time. So this is the formula for permutations. And here, guys, the order matters. So example, I have 3 letters, A, B, and C, and I would like to know how many 2-letter arrangements are possible. Order matters. I use this example, guys, because this is good to visualize what they're talking about. Because this will be a little bit different than with combinations. Here, the order matters. Okay, so we have AB, right, because I want to get them 2 at a time. Or BA, right, because AB and BA are 2 different orders. We have AC and CA and BC and CB. So there's 6 possible arrangements. Okay, now, and we use a formula, it's going to be n permutation 2, which means 3 factorial over 3 minus 2 factorial, which will give us 3 factorial over 1 factorial will give us 3 times 2 times 1 over 1. The answer will be 6. This is using the definition or the formula, and this is by actually like a visual. Or you have 3 letters and one arrangement on 2 guys, you're going to put 1, 2. How many can go here? Is 3. How many can go here will be 2. So the answer is 6. So only the permutations have two different ways to get the answer. Okay, example number 40 from page 478. From a cooler with 8 cans of different kinds of soda, 3 are selected for 3 people. And how many ways can this be done? Okay, we can use the formula. So it's going to be 8 permutation 3, which will be 8 divided by permutation 5. 8, I mean, it's going to be 8 factorial over 5 factorial. It will give us 8 times 7 times 6 times 5 factorial. The 5 factorials, they cancel or they become 1. So we're left with 8 times 7 times 6. So that's my answer is 336. Or we could do it this way, right? You have 8 cans and 1 arrangement and 3 right. So we're going to put 3 lines. So 1, 2, 3. How many can go here? 8. Right? Because they selected 1 kind of soda. If that's what's already selected, so 7 are left. And they select another one, right? And they already drank it, right? Or they already gave it to the people, right? Then there's 6 left. So 8 times 7 times 6 will be your answer, which is 336. Now combinations, okay? Let me show you the difference between combinations and permutations. So we have the same scenario, right? I have 3 letters, A, B, and C. I would like to know how many 2-letter groups are possible. Order does not matter here, guys. Again, order does not matter. And here's my formula. But let me show you a visual about that. It can be AB, it can be AC, and it can be BC because AB and BA are the same, right? Because order does not matter. So the answer is 3. Now let's use the formula. So it's going to be 3 factorial divided by 2 factorial times 3 minus 2 factorial, which will give us 3 factorial over 2 factorial times 1 factorial. Will be 3 times 2 times 1, 2 times 1 times 1. So we're left with 3 over 1, which is answer is 3. You see the answer is 3. So this is a visual, and I only use three letters, 2 at a time, because this will be easier to actually see. But now you're able to use a formula. Okay, now this is number 46. I think we're almost done. We need about 2 or 3 more examples. Number 46 on page 478. It says 4 items are to be randomly selected from the first 25 sets from the 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? So it's going to be 25 combination 4. Okay. Right? This will be 25, 24 times 23, and so forth. Why do we stop at 21 factorial? Because here these will cancel out. Right? That's equal to 1. Now, 4 times 3 times 2 times 1 will give us 24. So we're left with 25 times 23 times 22. There's my answer, 12,650. Okay, now, this is to recap on permutations, right? This is my formula, and these are the clue words. Arrangement, schedule, order matters. These are clue words for permutation. For combination means group, committee, set, sample, order does not matter. These are clue words for combinations. Okay. Now, there's a number 59 on page 478. It says a lottery game requires that you pick six different, I forgot to put here numbers, six different numbers from 1 to 99. If you pick all six winning numbers, you win $4 million. How many ways are there to choose six numbers if order is not important? So that's going to be a combination for A. Okay. So it's going to be 99 combination 6. There's my solution, which is what? 1,120,529,256. That's a lot. Now for B. Right, order matters. So that's going to be permutation. So again, I believe it's going to be a lot more. You see, it's 806,781,064,320. Okay, now number 60 on page 479. In exercise 59, if you pick five out of the six numbers correctly, you win 5,000. In how many ways can you pick exactly five of the six winning numbers without regard to order? Which means, right, it's going to be a combination. Here we go. Right, 5 out of 6. So it's going to be 6 combination 5. Now, remember, the lottery, we need to pick 6 numbers from 99. So, right, if we already got the 5 out of the 6, right, so it's going to be 1 out of 93 is left, because 5 and the 1 will be the 6 from the winning numbers, and 6 plus the 93 will give us the 99 total numbers that we have to choose from. So it's going to be 93 combination 1. Yeah. Again, 99, and this is my 6 right there. So these two must equal to right to 99. The first two and the second two must equal to 6. So 6 combination 5 will be 6 times 93 combination 1 will give 93. So 6 times 93 will give us 558. Okay, okay, now, let's see here, number 58. A financial advisor, but here, guys, I forgot here, let me see here, how many ways can you pick? Okay, that's the answer there. Number 58. A financial advisor offers 8 mutual funds in high risk category, 7 in moderate risk category, and 10 in low risk category. And the investor decides to invest 3 at high risk, 4 at moderate risk, and 3 at low risk. How many ways can the investor do this? Okay, so let's do solution. Okay, if you read the problem carefully, order does not matter. So for the first one, we have 8 mutual funds in high risk. We want to get 3. So it's going to be 8 combination 3. Then in moderate risk, we got 7, right? We're going to choose 4. It's going to be 7 combination 4. Then lastly, we have 10 in low risk, and we want to pick 3. So it'll be 10 combination 3. 8 combination 3 will give us 56. 7 combination 4 will give us 35. 10 combination 3 will give us 120. We multiply those out. It's going to give us 235,200. So these are all the possible ways that an investor can do this. Okay. I believe, guys, that's it for this PowerPoint. Thank you. I believe I went like 25 minutes extra, or almost 30 minutes extra. I'm sorry about that. But I truly believe this was important to cover all this material, because next week is the last week of class for the 1324. Thank you.
Alrighty. Thank you so much to Mr. Sassi for presenting the material today. Probability and sets are a little bit complex, so thank you again for going over that material. Thank you to our audience for coming and being a wonderful audience. We hope that your summer semester has been going by well, and as Mr. Isasi said, next week is the review for the final exam for both 1314 and 1324. So we hope to see you next week, and I hope your summer semester has been going by well. Thank you again.